Well, hello all. The South African grade 12s just 2 hours ago or so wrote the Physical Sciences Chemistry Paper 2. And I'd like to just go through the paper and just give my impression, my tuppence worth for what it's worth of what the paper was like. So, ignoring the multiple choice, which are question one, we come to question two, which is naming all these various compounds. So I ask myself, in my life, has naming the compounds ever helped me? Will it help them? I think it'll only help them if they go to university and do organic chemistry. So, for one or two students out of the whole batch of matriculants who go into organic chemistry, naming these organic compounds is maybe going to help them with their university, but why not just name them in university? Now, I'm prejudiced. I love organic chemistry so I'm kind of trying to see, would all this stuff naming, actually knowing your alcohols, your esters, your ketones and aldehydes, and all the various types of organic compounds, your haloalkanes like this one with bromine there, is it useful in a normal life? And I have to conclude no. So basically, although nice to know and a lovely mental exercise, I can't see any value to this. That 99% of the physics chemistry students will ever use this. So let's go to, so there they ask questions: unsaturated, saturated, 4 mile group, for example, the aldehydes, etc., the UPAC name. So it's nice to name these. What are isomers? Okay, so let's go, and then they talk here about carbonic acid react with another thing. So they've done this practical of making an esterification reaction, and they know that an alcohol and a carboxylic acid were involved in making the ester, and then there's some naming. So I have to say, like I can say about the physics paper one, it was if I was teaching the kids this year, I would say I liked the paper one from their point of view. It wasn't too tricky, and I don't think this paper two is too tricky. So let's go on to the next question. Here are the vapor pressures of different organic compounds. Let's see if we can get a better view of there are the various compounds, and then this is how easily they evaporate. And the kids know that the shorter the chains and the fewer the oxygens it's got, the quicker they evaporate and the higher the vapor pressure. So there's a way of working out for each compound in the order in which they will evaporate, and normally the alcohols and the carboxylic acids have got a low boiling point and a very low vapor pressure. They don't boil at high temperature. So I think this could be useful, knowing the boiling point of various organic compounds and their vapor pressure. But have I used it in everyday life? No. Is it going to help solve South Africa's problems, knowing the boiling points and vapor pressures of various organic compounds? They're never going to come into contact with any of these pentane, 2-methyl butane, 2,2 dimethyl propane. They're not going to come into contact with these in their normal life. So will it help them? My word, when I think of all the things in the universe that involve chemistry, every compound that we eat, touch, taste around the house, plastics, fuels, etc., and these common household chemicals, and saying, can't we just name those and give their properties and their uses and reactions with them, instead of this highly theoretical but utterly useless stuff? As I say, I'm quite biased, because I do actually like this stuff. I mean, obviously I enjoyed teaching this stuff for 46 years. So here we've got an organic compound, and undergoes cracking, which means the long molecules split into smaller molecules, and then it undergoes halogenation in here, and then it undergoes elimination, and it forms a unsaturated compound here, meaning having double bonds and so on. So they ask questions. So they're playing around theoretically with different molecules, adding this, adding that, and you get your addition, elimination, and substitution reactions, which they're testing here. Again, they will never use it. I've never used that in my life. No, never. You can go through life without using it unless you're in a very limited field. Cracking is, for example, what, say, Cecil might do with coal or oils to make them into lighter oils, to crack them, make them smaller, more volatile, and, making certain petrochemicals, maybe. But, I mean, again, how many people our students are not going to be, one student out of this whole batch will maybe go and do that. So the rest of this is just theoretical. And then they ask all the questions regarding the substitution, addition, elimination reactions. So I can't say that it's all that useful. I think this is just a repeat of, then they ask about isomers. Yeah, it's just a repeat of the same on the next page. And then there's a few more questions about giving it's always nice. I mean, you need to know structural formulae, you need to know chemical formulae, etc. UPAC names are nice, but I mean, out of all the things in South Africa, couldn't we go and look at, as I say, recycling? All the names of the plastics, what we can do, what's their boiling point and their melting point, can we make with this plastic? Is this plastic? And I mean, maybe people could get a living out of recycling plastic. Anything practical, but this is just impractical. I've never used it. They will never use it. If they go to university and they specialize in a tiny little field of organic chemistry, they may use it. As I say, that's my frustration with this, is how useful is this stuff? So this is question number 5, I think it is. It's a bit hard to read that. This is the reaction of aluminium with hydrochloric acid. Now, this is a reaction that we used to do in class. We would throw aluminium cans into hydrochloric acid. We'd pump the hydrogen that's given off into a balloon. Then the balloon float to the ceiling, light the balloon, bang! I remember burning the hair off my hand, nearly raising the ceiling. Okay, so it's a lovely reaction. And I guess you could make hydrogen this way, and it's fun and everything. And it's got the rates of reaction that you're dealing with here. But again, what they're doing is they're really going very highly mathematical. They're going to ask you, okay, so collision theory, nice to know. If you increase the acid to 2 moles instead of 1 molar solution, moles per decimeter cubed, you're going to increase the reaction rate. That curve is going to become greater, etc. Reaction rates are important, but not, and this is not a bad reaction to take cans and add them, aluminium and or metals, add them to acid and form hydrogen balloons, full hydrogen balloons, and make hydrogen balloons. I mean, it's fun, but who's in the business of making hydrogen balloons in real life? So, as I say, I love all chemistry. I've done this many times, but is it useful? Not really. So, although the theory is fairly useful, but again, they always make it super highly mathematical. Maths has been captured by the physics and chemistry have been captured by the maths people, because they hire maths/physics teachers. So all the teachers these days are maths/physics teachers. So that they just love maths, and frankly, they want to make physics a department of maths. So all this has got so much maths in it, which is totally unnecessary. Anyway, here's the Maxwell-Boltzmann curve. I think I can't read this, and then they've got curve X and curve Y, and here's the kinetic energy. So they've added, it seems, a bit more energy to curve Y, and that's why you're getting more molecules that have got more energy. And this was the cooler molecule, so they've added energy. And what was the change made to Y that was heated up? Is it useful? Have I needed to know this curve? No. I haven't seen one thing yet that would solve South Africa's problems or prove practical. Not one. And then here we've got a reaction, and we've got what happens when you add, here you've added oxygen and and it spikes. So here's your reactant, and then Le Chatelier's principle of how the reaction comes. This is in a sealed container, comes back into equilibrium, and it's nice, and I like it, and I've taught this so many years, and this is actually quite nice. I mean, it's done quite. If I was teaching these students, I'd be quite happy with this paper. Um, and then they ask questions on what has disturbed the equilibrium, and you can see every time the equilibrium comes back into equilibrium, then they add this or they subtract that, and then everything readjusts again. So, is Le Chatelier's principle? It's nice to know. I like it, but it's useless. The only place I've ever thought of Le Chatelier being of practical use is if you take a bottle of fizzy water, carbonated drink that is an equilibrium of carbonic acid, and carbon dioxide. And if you take the cork off and release the pressure, then it favors the gas reaction. And if you cool it down, it favors the carbonic acid reaction. So, is have I ever used equilibrium other than in fizzy drinks? And nobody in using fizzy drinks even thinks of that there's an equilibrium somewhere there. No. So, nice to know, but absolutely worthless in practical life. And here is a reaction. They've got the equilibrium constant, and here they've got to play around with a number of moles. So this is balancing reactions. How many moles of this react with how many moles of that to produce how many moles of that and how many moles of that. And then they start a table. You've got your start, used up, or made, and then you've got your final products, and then you've got the concentration. So you make this little table, and then you fill it out, and it's all highly mathematical, and it can be useful. I mean, being able to know how much stoichiometry, how much of this react with how much of that to produce how much of this and so much of that. I think it is important. I think it is great, and I think people could use it, especially if they were trying to make some product and they had to work out how much. Say they were going into the business of making carbon dioxide, or let's say sequestering carbon dioxide and turning it into water and CO. Okay, that's a useless reaction. So again, there's not much here that we can actually use. Say they were making hydrogen from this reaction, and you wanted the hydrogen, well, you couldn't separate it from the CO2. So, okay, so this is basically a worthless reaction. It's useless, demonstrates a principle. Question 7, we've got titrations of acid and bases. So sometimes they do a titration. Generally, they just do one practical, which is making an ester. Sometimes they were given the choice of titrating. I think titrating acids and bases is quite a useful function. I think that because if you spill an acid, you can know how to mop it up with a base or something. So you could work out exactly if I had so much acid and I mixed so much base with it, I would get so much. It's again like stoichiometry. So it's kind of, stoichiometry is the ratio in which things combine in a chemical reaction. So titrating, meaning dripping acid, mixing acid and base, neutralizing it and getting an equivalent point, and then which indicator like methyl orange. Well, if you've got a strong acid with a weak base, you're going to have an equivalent point in the lower pHs, and that's where your methyl orange obviously reads. And then dilute acid is mixed with magnesium. So this is almost similar to your aluminium with hydrochloric acid. And now this is redox. Which is the oxidizing agent? Which is the reducing agent? I think this is important. Are these particular reactions important? No. But so they could so easily choose practical, real, useful reactions that are used in everyday life. For example, in your geyser, you've got normally magnesium, and then it will be a sacrificial anode, and it will slowly decay away. Maybe you could. That actually comes with another question. So, knowing which is the oxidizing and reducing agents, and what is oxidized, what is reduced, is this is important. Whether these reactions are important. Will dilute nitric acid react with copper at yes or no? So here it is observed that dilute hydrochloric acid does not react with copper at 25. Explain this observation by going to the relative reducing agent. So you go to your redox table and you look it up. Will it react with copper solid at 25? Yes or no? I think they just said it wouldn't react. Am I struggling to read here? It is observed that dilute hydrochloric acid, nitric acid, so they've got hydrochloric acid and then nitric acid. So you presumably got to go and look up where the nitrate sits on the table, on that redox table, and see whether it's higher than hydrogen or not, and then see whether it will react or not. So yeah, I think it is important to know that redox table. And then here they've got a tiny little question on galvanic cells. These are cells that produce electricity. It's worth 4 marks out of the whole 150 marks. And this is possibly making a cell, a galvanic cell or voltaic cell, that can produce electricity, is perhaps the most useful thing that we could do. And yet they're given it 4 marks. Okay, I like that. But it's only worth 4 marks. And here they've put a piece of silver in a lead nitrate solution. They want to know whether the silver will get gobbled up by this lead nitrate solution. And again, you go to your redox table and you see, is silver or silver is that country AG, is it higher on the redox table? Is it closer to lithium than lead? If it is, then it will get spontaneously eaten up. If not, if it's lower than lead, and this is lead, divalent lead, Pb2 plus lead. So you look for that half reaction, you see if that silver half reaction is higher, closer to lithium, then it'll tell you whether it is eaten up or not. And then they ask questions here. You've got an electrode. These electrodes are made out of, I think they said out of carbon, meaning charcoal. So you've got charcoal, a battery, and you've got salt. And here you make sodium chloride on the one side and you make chlorine gas on the other. They kind of have studied this quite a lot. And then you've got to tell which is oxidized, which is reduced. So what's going to happen is the sodium ions are going to be chased to this is your negative side. So the sodium ions will come there. They will gain an electron. That's reduction. And the chlorine ions will go to this positive side. They will lose an electron. And that's oxidation. So oxidation reduction is quite important. And this actual reaction is used in swimming pools to make chlorine, etc. And you can make sodium hydroxide. This is there's a bit of a useful reaction here. And you could substitute a solar panel there. And so I think that was the last question. I think that's all there is to it. Yeah. Oops. So that is the last question. So here I've been through the whole paper. I've just given it a look over and just asking myself this question. Will this help the majority of students who are going to university, who are never going to see this stuff again? They're not going to do chemistry and physics. They're not going to do pure chemistry or physics. They just want to pass physical sciences to get into some field, like they want to become marine biologist or something. And to do that, they need to have done physics. I doubt whether we will see more than one or two out of the whole batch of people who go to university and actually study physics and chemistry or organic chemistry and like this. And even so, even if you go to university, where are you going to find a job? What jobs are there in South Africa that are going to be using this stuff? Whereas, I mean, I could go on for hours about chemistry is so useful. Everything we use in the household, you could take reaction like you throw you drain cleaner, sodium hydroxide down the drain, and it turns the fat in your drain plug into soap. So let's make soap. Making soap is far more useful than anything I saw here. So let's make soap as an example. Or like this last question, let's do electrolysis of solutions like the sodium chloride solution. Let's see what we can make. Let's make our sodium hydroxide, which goes into soap. So that is what this reaction is using. And as I say, combustion, how about the reaction that goes into combustion, how to make smokeless fires? What is it that South Africans need? I just actually wrote, I just kind of, now I'm going to go on a rant, I wrote all the alternative things that we could do in South Africa instead of this syllabus. We could do soap making, we could do hydroponics, we could do forging, plastic molding, plastic identification and recycling, programming microcomputers, making audio amps, glucose in a test for, we could, as chemistry, test people's pee or urine and see are they diabetic or not. What about all the tests for different substances? What about, I'm trying to struggle with my own writing here. Solar installations, building cement, building kind of chemical reactions in building, like cement, letting it stand for time, how much water, how to make strong cement. There's so much chemistry that goes into that. What about infrared? I'm combining physics and chemistry. For CCTV and other cameras, what about controlling motors? This is physics. They used to do fertilizers here. Why not send the people to the land? Teach them about fertilizers, NPK. They used to have it in this paper a few years ago. They took the only useful thing that South Africans could use. Send the people back to the land to farm. Water harvesting and pumps, charcoal making, alien vegetation clearing, and the type of firewood and what its use is for cooking. So cooking, burning the stuff is a chemical reaction. Rocket stoves, for example, smokeless stoves, drone flying, stats. What about doing scientific experiments and asking people to formulate scientific experiments, even if they're theoretical, from data on the internet, or just, I didn't see anything here that involved a hypothesis and trying to find relationships. Water purification and testing. We have very impure water. What about the chemistry of water purification? Bridge building, that's part of physics. I'd say get them to make a pedal electricity generator, that's physics. Smokeless fires, and I've said research. What about making timers or fixing appliances, wiring a house, putting on a plug, night light, on-off circuit, plumbing, wiring a house, fermenting, I've just thought of that, fermenting alcohol, it's a chemical reaction. Make them do things, have it like a Scout proficiency badge. Once you've brewed a batch of alcohol, you get a badge, your alcohol brewing badge. What about bow drill, fire lighting? Surely there's some use in that. There's so much to know, like even a fire, if you've got your reactants and in their fine powdered form, they're going to the oxygen's going to get in there, and you get a fire, and you blow oxygen, and you're adding another reactant, and your product is going to be carbon dioxide and charcoal, and that charcoal and water, so eventually going to, and heat. What about distillation? Distilling like alcohol, and what about flamethrowers? What about flame color testing elements? What about welding? Wattle and daub making? What about how to waterproof houses that are made out of wattle and daub and mud? That's chemistry. Hydrophilic and lipophilic substances, things that love fat and things that don't. What about solubility? What things will dissolve in what things? There's nothing here about solubility. Cooking temperature physics, boiling points, hardness scale for various things, solar tracking, soil fertility. My son's got a little soil fertility tester. Water, how wet is your soil testers? Get the kids to make these things, or to work with these things. Reaction rates. Make a what have I written here? Oh yeah, that reaction there, making sodium hydroxide and chlorine. I actually wrote that down in there. They've got useful reactions like drain cleaners. Or what about making a waterless urinal? Household chemicals and their dangers, ammonia and chlorine, for example, sulfuric acid and water, etc. Sacrificial anode in your geyser. What about making gunpowder, stink bombs, glass blowing, pottery making and the chemistry there, LED circuits, simple transistor circuits, hand water pump, make a soil moisture sensor, rain gauge, and keeping rain data. I mean, say you monitor the rain every day and you keep that. That's science. That's teaching the kids to be consistent, and then draw a graph of it, and then they know what the rainfall was for this year, etc. Computing acids and bases, what's their use in life. Doppler, as far as the age of the universe. Real trajectories, not vertical projectile motion, throwing things in both, not just up and down, but in two planes. Rope making, forging, welding, I think I already said that. Making a penny stove, get the kids to make an actual motor. I've mentioned solubility, the various glucose and keto tests. Dam building, water pressure, levers and trebuchets, etc. Building science, boiling and cooking fuels, preserving cooking, pressure cooking, how to preserve, what chemicals can you use to preserve. All these things I see as far more useful than anything I saw in this paper. Carbon sequestration, how do we get carbon out of the atmosphere? And you know how you can do it? You just take plants, trees, you turn them into charcoal, you use the useful wood gas that's given off, and then you bury the charcoal in the ground, and that becomes biochar, and that lasts 1,000 years. Let's teach the kids that sort of chemistry. Take all your alien vegetation, burn it. Don't burn it with the smoke. Use that wood smoke to cook with, etc., and then dampen the fire before your charcoal burns, and then put it into the soil and it becomes biochar. That's carbon sequestration. And we also trying to get rid of pit toilets and so on, but why not just use the human poo, dig a hole in the ground, build the toilet on a hill, let the poo run into a hole. The moment the hole gets filled, plant a fruit tree there, cover it up. Done. Who needs water flushing toilets? I'm just thinking, or I'm just giving you some of the things that I just sat down and made a list of that would be more useful in both paper 1 and paper 2 if they'd include any one of these things or any of these skills. And actually, again, I'm telling you, the kids have not touched anything apart from perhaps making an ester. That's the only thing they've touched in this chemistry. And in the physics, what would they have touched for their physics experiment? I'm not even sure. Probably finding the internal resistance of a battery, and utterly worthless. I've never in my whole life cared what the internal resistance of a battery is, of a little AA battery. So, I mean, or maybe they did a titration. I very much doubt it. So they probably made an ester. South Africa, you're in such problems. And as I say, we all went to school with this Western education, which is so wasteful. And you said, oh, it was fine for me. Oh, it was dead right for me. I've lived all my life with my education. But now we have kids, 50% of our South African students are not getting jobs. That is the problem. And they're not going to find a job with this knowledge. There's nothing out there that you know from this paper that's going to get you a job. Maybe you'll go to university. What about the kids who don't go to university? What about the kids that drop out? So why not just teach them useful stuff that 100% of the kids are going to use for 100% of their life, and let the universities worry about those few students so teach useful chemistry. Maybe they need physics lit, like they have maths lit, useful practical chemistry and physics. So they need physical sciences lit. I don't know. As I say, if my kids were writing this paper, fine, but actually this paper's garbage. Just like paper one is, it's useless. It's not going to solve South Africa's problems. So that's the bad news. Sorry.